So today's lesson is the first of a new unit. Your textbook organizes it slightly differently. Your textbook puts circular motion in with the energy unit. And I'm going to take circular motion out of the energy unit, and I'm going to throw it in this unit here and make this unit slightly larger. And it'll make the energy unit slightly smaller at the end. I don't think it'll make a difference, but if you're wondering why we're not going in order of your textbook anymore, I think this is going to fit better. So I'm going to call this unit oscillatory motion, circular motion, and waves. And so let me kind of describe where we're going this unit. Okay. Many of the things that we've been working with are really closely related to math. I hope you guys have noticed that. Linear functions, quadratic functions. Anything that's a projectile is a quadratic because it goes up in the air and falls back down. Okay. Well, those aren't the only functions we've ever covered. Okay. And so my goal in this unit is to introduce to you a new type of function, which actually I don't think any of you guys have learned yet in math. My grade 12s, though, we're going to start covering it later in about a week and a half. And they're called periodic functions. Okay. So grade 11s, don't freak out. You don't need to know every little detail that we're doing in math, but we will cover, I'll give you enough information that you'll be fine, okay? So the two main types of periodic functions are either known as sinusoidal functions or circular functions. The main examples I want to give you of what we're going to talk about, oops, wrong way. Let me come back to that, are either going to be pendulums or springs. Those are the main ones so far. Okay. Think about how a pendulum works. It's going to go back and forth and back and forth and do that for, well, in theory, until friction finally can find a way to slow it down a lot. Okay. A spring kind of works the same way, only the spring might bounce up and down and up and down and up and down. Okay. That motion is not really linear and it's not really quadratic. It's known as periodic motion because it goes back and forth according to a period. Okay. Here is an example of a graph that we're going to learn about in math in a little while for you guys in my grade 12 class. This is known as a sinusoidal graph. Okay. What does it look like in everyday life? Yeah, a wave is a good way of putting it. The first slide I threw on like a picture of like a wave pool. Water. Like if you were to drop like a pebble into water and it ripples, you know what I'm talking about there? That would happen according to a wave. I've got more examples later, but this is a kind of graph where it goes up and down and up and down and up. And it'll keep doing that for forever, I guess, unless friction takes hold. Does that make sense at all? Okay. Imagine a pendulum. A pendulum's going to swing back and forth and back and forth. Okay. We're going to start with that, and then after we cover sinusoidal motion, then we're going to start making our pendulum do this. You can see that. Hopefully you guys can see that. We're going to start with just side-to-side motion, but then if we start going all the way around in the circle, that's circular motion. Does that make sense? So my thought process here is, let's start with like a partial circle. If I can find one here. Here is the start of a circle, and then eventually we'll then have this pendulum swing all the way around in a circle. And our goal is just to discover how motion happens in like circular patterns, non-linear patterns. Does that make sense? Oh, they left. Okay, I'll keep going and that's why I'm taping it, I guess. So far, so good? Okay. So we're still talking about motion. We're still going to be using kind of kinematics formulas. For sure, we're still going to be using dynamics formulas, just rather than it going just that way. Now it goes bounce back and forth like a spring. Okay. You know that curve I showed you, that wave kind of curve I showed you right here, okay, which grade 12s, keep this in mind, that's where math is going in a little while. So this makes sense. As a pendulum goes back and forth and back and forth, if I were to turn this curve on its side, do you guys see the relationship here when it goes back and forth and back and forth? This is the pendulum swinging back and forth. Can you guys see that relationship there? Sean?
And the time is probably just the y-axis?
Yeah, like this would be distance, and this would be time. Does that make sense? And so this is just a new type of function that we'll learn about. So basically my goal today, a very introductory topic, I want to introduce two terms that you need to know and be fairly comfortable with using. Okay. The two terms are period and frequency. Okay, so here's some definitions. I'll just read off of here. Period is how long it takes an object to make a cycle. So if you had a pendulum and I pull it all the way out here and then I let it swing there and back, that would be one cycle. Does that make sense? There and back, another cycle. So if I were to go to like this picture right here, let me just erase all this stuff. Period would be described as from here until here. Does that make sense? Because it went all the way out, all the way back the other way, and all the way back. That would be one cycle. That makes sense? So that would be period. And then this would be a second one. That makes sense? Okay. Period is denoted as capital T, which I actually gave you guys as one of your questions on your unit test. I just kind of threw that one in there at you. I believe it involved circular motion. It was VC equals 2 pi r over t. You guys remember that one? Yeah, your goal was to solve for t. T stands for how long it takes for a cycle to happen, which basically in that example was how long it takes the International Space Station to go all the way around the Earth once. Okay. So, it's usually measured in seconds. I don't know why there's a period there. That looks really weird. Denoted. So, anyways, measure period in seconds though. Okay. Frequency is similar, only frequency is the number of cycles you can have in a second. There are some things, lots of things to be honest, that happen like very, very quickly. And so it's better not to measure how long one cycle takes, but to figure out how many times you can do that in 1 second. The best example I have for that is RPMs. You guys know that term? Like RPMs would be like a term you'd use in your car. It's how often like the pistons go up and down in your car in terms of making your engine rotate. That makes sense? 3,000 RPMs means that that piston goes up and down 3,000 times in 1 minute. Okay. So it's similar, but it's a bit of a different type of unit. This is measured in either what's called a Hz, called a hertz. You guys ever heard that before, hertz? Or sometimes we call it seconds to the -1. Grade 12s, what does -1 mean?
Inverse.
Reciprocal.
Oh.
Close. Okay, so as a reciprocal, we're going to learn about this in a week, okay? Just so you guys know. If I ever give you a -1, it means 1 over seconds. Okay, what 1 over seconds means is that's how many cycles, like, my board just died. Come on, there we go. 1 over seconds really refers to like cycles per second. So that's like how many times it happens in 1 second. So we're gonna do some examples of this. A couple more thoughts before I do that though. Here's some applications to everyday life. Okay. These are some more examples of like periodic sinusoidal curves. So imagine this is like, turn it on its side, it's a pendulum going back and forth. Which pendulum is going fastest? The bottom one, it has the highest frequency. Right? And maybe you've heard the term frequency used in other capacities, like for example, radio waves versus X-rays versus light waves. You guys ever study electromagnetic spectrum in like grade 8 maybe? Is that something that you're familiar with? We're going to do it more in grade 12, but like radio waves might have a lower frequency compared to UV radiation. Long story short, the tighter the wave, the higher the frequency. Hey, Noni. It is. Okay. A couple more definitions I need you guys to know here. Period and frequency are inverses of each other, but they form what's called a reciprocal relationship. And so a reciprocal relationship means that like the graph looks like this. Okay. Inverse is a tricky word though, because when we talk about, because you weren't fully wrong on that. Inverse just means in math though, it means we flip x and y around. But in physics we should really use the term reciprocal, meaning that it's like one over top of another one. So as the frequency goes up, the period should go down. What other graph have we done recently that has this sort of relationship? You guys remember?
In that lab, the one that was between this and squared and
Good. Yeah, it was about your distance squared and force, and hopefully you made a graph in one of your labs that was like this as well. That has the same sort of relationship. Okay. Okay, 2 more examples, then we'll do some actual math work to it. Here's some more examples of periodic relationships that I kind of found on the internet. I just snagged some graphs. This one right here, though, is probably the most common one you could imagine. Anyone know what this is? It's a heartbeat monitor. In theory, your heart should beat in a very periodic fashion. It should beat consistently every blank seconds. You guys ever heard the term like beats per minute? Beats per minute would be the frequency. That makes sense? Whereas how long it is between heartbeats, that would be the period. Let me see if I can give you an example. If my heart beats at 60 beats per minute, 60 beats per minute is the frequency. Okay. If there's 60 beats per minute, how long in between every heartbeat? 1 second. So 1 second would be the period, and the frequency would be 60. Does that make sense? This actually has huge applications to one particular field that I know, and it's where my wife works. If you guys don't know, she works on labor and delivery, which is like where they deliver all the babies. And I found an example of a fetal heart monitor tracing strip. Have any of you guys ever seen one of these before? Okay, let me describe to you how this works. What they do at the hospital, I've been through this twice now because Melissa's given birth to both of our little girls. They usually want to put mom on some monitors to keep track of a few vital signs. One of the signs they got to keep track of is the baby's heart rate. Okay, and one of the reasons why that's important is that if the baby is going, like when it's being born, if the baby has got a really high heart rate or a really low heart rate, it usually means something is wrong. Does that make sense? But if the heart rate is very consistent, that usually is a good thing, and it means that you can keep going. But hypothetically, the baby's heart rate rises all of a sudden, then you need to have a C-section. You guys know what that is? Like where they cut the mom open to get the baby out? Okay. Same thing could happen if you have the baby's heart rate drop. This actually happened to us with Cami. When Cami was being born, every time Melissa had what's called a contraction, which by the way, these things down here are contractions, Cameron's heart rate was dropping like crazy. And we realized later the reason why her heart rate was dropping was because the cord, her umbilical cord, was around her neck. And so every time the baby was trying to come out through a contraction, it was squeezing her neck, thereby causing her heart rate to drop. Well, because of modern technology, the doctors were able to recognize this and realize that we couldn't keep going the way we were going, and so Melissa had to have a C-section instead. So thank goodness, because both mom and baby were safe. If we hadn't have done that 100 years ago, there's a good chance Cami would have died. So, anyways, that's an example that's near and dear to my heart, where because of being able to recognize these sorts of patterns and recognizing regular contractions and regular heartbeats, as soon as like Cameron's heart rate all of a sudden dropped like this, it probably would have happened here, right? Like here's her heartbeat, and then as this contraction happens, it dipped. That gave the doctors and the nurses the ability to know something's wrong. That makes sense? Anyways, I wanted to share that example because that one obviously matters to me. Let's do some math then, and then we'll call it a day. Here's a typical example. A hard drive in a computer spins around in circles. The faster it spins, probably the more powerful the motor, right? Probably the better the computer. So if you have a hard drive spinning at 7,200 RPMs, let's figure out its frequency and its period. So first thing, what does RPMs mean? Sure, revolutions per minute. Rather than calling it revolutions per minute though, you might want to call it cycles per minute. That might work better. So first thing, let's figure out frequency. Frequency is measured in cycles per second. How do I convert this into seconds? Close. You've got to do minutes on top and 60 seconds on the bottom. Do you see how the minutes then would cancel? So if this thing goes around 7,200 times in a minute, how many times does it spin in just 1 second? Okay. So that would be 120 cycles in 1 second, or the more common way of noting this would be 120 hertz. So that's for frequency. So we would denote that with F. Okay. You could also denote this as 120 seconds to the minus 1, which just means that this goes around 120 times over 1 second. For those of you guys who know how minus 1s work, we're going to do this in about a week and a half, grade 11s. Just so you know. That makes sense so far? Okay, then to find period, there's a formula for it, which I kind of glossed over. It was back here. T equals 1 over F. This is on your data sheet, just so you know. So if you can find frequency, then T equals 1 over F. So then if you have 1 over 120 seconds to the minus 1, what's 1 over 120? 0.0083. And then based on sig digs here, this one here had 4 actually. So I should have said this was a 120.0. And then I get to keep that many seconds. So what this means then is that really short amount of time, that's how long it takes for the disk to spin once. Quick thing I want to show you guys. Whenever it comes to this right here, there's a button on your calculator that can help with this. It's this -1 button sitting right here. You guys ever use that? If you were to do 120 and then go to the -1 like that, that is going to be 1 over 120. So you can just use this button right here. This button basically makes something a reciprocal. So rather than doing 1 over 120, do 120 to the -1, and that basically makes it go 1 over 120. Easy? Cool. One more example, then we'll call it a day. Let's look for the period and frequency of these, hopefully like fairly everyday life examples. So first, what's the period and frequency of a minute hand of a clock? Does the minute hand of a clock have any sort of pattern to it? It goes around in a circle. So how long does it take the minute hand of a clock to get back to where it started? The minute hand of a clock. An hour.
Okay. I meant like the tick.
No, because the little red one right there, the tick, 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 that's the second hand.
Right.
Right? So the minute hand goes all the way around after it's been 1 hour. So for this first one here, period would be 1 hour. Although we don't normally measure period in hours though. Nope, seconds. Seconds. So 3,600 seconds. So then to find frequency, period was supposed to be 1 over frequency. How do you rearrange this to get frequency by itself? Multiply f out and divide by t. So really frequency is 1 over period. So to find frequency, do 3,600 to the -1. So I guess you could call it 1 over 3,600 hertz. There are this many, really small number, cycles in a second. Is there even a full cycle in a second? No, it takes way more than a second for this thing to go around. So this thing's frequency is very infrequent. It does not happen quickly, which is why its period is so large. The larger the period, the smaller the frequency. Going back to this graph right here, if you plotted period and frequency, the larger the period, the smaller the frequency. Does that make sense? Okay, let's do a person with a heart rate of 86 beats per minute. 86 beats per minute is already kind of a frequency. It's 86 cycles per minute. But we don't want it per minute, we want it per... Okay, so take minutes over 60 seconds. Okay, so if you took 86 cycles per minute and divided by 60 seconds, what would you have? 86 divided by 60? Okay, so you have 1.3 cycles per second. 3 repeating?
No, 4-3.
Oh, 4-3, thank you. Okay. Is that a period or a frequency? It's a frequency. Whenever time is on the bottom, it's a frequency. It just takes some time to get used to. So we've now solved for my frequency. So you could call this 1.4 hertz. Now to figure out period, which is how long does each heartbeat take in terms of time, I mean, I can do some mental math here. If you do 86 beats per minute, that must mean that like if it was 60 beats per minute, it was 1 beat per second, right? But if you have 86 beats per minute, it must be like slightly under a second. Does that make sense? So to solve this, for period, you could basically go 1.4 to the minus 1, which is like 1 over 1.4. What do you get? 699.
Did you not get
Make sure you use the actual 1.43 number as well. Don't use that rounded number.
I got 0.69767. Yeah, so.
Okay, so is that 0.70 with rounding?
Yeah.
Okay, so what this means then for period is every 0.7 of a second your heart beats. The other way of looking at it is your heart beats 1.4 times per second. Let's say it one more time. 1.4 times per second your heart beats, or every 0.7 of a second your heart beats. It depends on how you want to look at it. Right? So your heart basically beats just more than like
once?
per second. Does that make sense? Okay. The Earth. That was very non-specific there on purpose. Does the Earth do anything that is cyclical as a pattern? Okay, it rotates. And it goes around the sun. There's actually 2 different periods and frequencies we could figure out for the Earth. So for one of them, the Earth like rotates. How long does it take the Earth to rotate? 24 hours. Yeah, that's one way of looking at it. So one way of looking at it is you could say that, what is 24 hours multiplied by 3,600 seconds in an hour? Is that right? I need help with the calculator here.
86,100.
Okay, let's put it in scientific notation. So 86,000 would be 8.6 times 10 to the 4 seconds. Is that a period or a frequency? Is seconds on the top or the bottom? It's on the top. This is a period.
I thought it said like something per second, 7
Sorry, this is 8.6 times 10 to the 4 seconds. So that's how long it takes the Earth to spin. So then to find its frequency, should the frequency be very high or small, large or small? Should be very low. The period of the Earth spinning is very large. Therefore, the frequency should be very low. So if I want to find frequency, frequency would be 1 over 8.6 times 10 to the 4 seconds, which is probably going to be a very small number. That'll give you the hertz. Anybody have that number for me by chance?
1.15 times 10 to the -5.
Thank you. And so that would be seconds to the -1, or you could call it hertz as well. So what that means then is the Earth cycles this amount every second. It's not very much. The other way you could look at Earth, though, is Earth also doesn't just rotate, it also goes around the sun. That'll be even worse, because the Earth goes around the sun once every 365 days. It's actually 365.24 days. You guys haven't heard this before. That's why we have to have like leap years. So like 365.24 days is how long it takes for the Earth to go around the sun. So then you'd have to times by 24 hours in a day and multiply by 3,600 seconds in an hour. Let's not bother doing the calculation here, but do you guys get the concept then? Once we solve for that, that would be the period, and then to find the frequency, go 1 divided by that period. One last example, then can you guys give me 1 minute?
Yep, we'll go to that.
Okay, thanks. We're just about done here. Bumblebee flaps his wings 800 times every 10 seconds. If you flap your wings 800 cycles in 10 seconds, what's different about this one here?
It's not 1 second?
Yeah, it's not 1 second. So if it's 800 times in 10 seconds, then would it make sense to make it 80 cycles in 1 second? Is this frequency or period? Frequency. It's just going to take a while to get used to the two of them. Okay, the reason why this one is frequency is that the seconds is now on the bottom. So you could call this thing 80 hertz. So 80 times in 1 second, this hummingbird goes. Was it a bumblebee or a hummingbird? One of the two. Same difference, whatever. Okay, so then to figure out how long it takes for the bird to flap its wings just once would be, so this is period. Frequency then would be 80 to the minus 1, or 1 over 80. So 1/80th of a second.
I thought the top one was frequency.
Sorry, the top one was frequency. This one is period, thank you. My bad. The math is the same, by the way. If you have frequency and you want to find period, 1 over top of. If you have period and want to find frequency, 1 over top of. It's the same either way. You just got to keep track of which one is which. So, what's 1/80th out of curiosity? 0.0125. So, every 0.0125 seconds, a bumblebee flaps his wings. Or, a better way of looking at it maybe is that 80 times in 1 second it flaps its wings, which is like crazy. Quick summary, then we'll go get breakfast here. So our goal now is to talk about things that are periodic in motion. Usually they either go back and forth, or like the bumblebee, up and down, or eventually we're going to talk about circles. So a very common term I need you to know is period and frequency, and just be able to tell the difference between the two. Okay, that's it. Go grab breakfast, hunt the cart down, and then take the rest of the class to work on your test. Thanks, guys.
We have brand muffins.